So let us begin in our exploration. I still have a bit of studying to do. I haven't fully studied this topic, so some of the videos might take longer to come out. I'm in the process of exploring the irrational numbers. So here's what I do know. There's no physical way to actually measure them. In this regard, I might need a bit of help from physics major friends because I'm not that good at physics. But what I do know is, well, quantum mechanics says that we can't measure any length smaller than the Planck length, which is 1.6 times 10 to the power minus 35. Very simply put, let's just say, let's just say that I have no way to verify what happens after 34 or 35 decimal places. If I have a number that has more than 34 or 35 decimal places, I have no way to know what happens after that. I can't measure it. Give me a length or give me a number. If you told me like, Ilham, here's the number line. Can you please point to the number 1 times 10 to the minus 40? I couldn't even if I wanted to. I just couldn't because there's no scale using which I could measure and plot a line right there. I couldn't do it even if I wanted to. So that's the thing. However, even though we can't measure and verify such small precisions, and in this case, well, I mean, you clearly understand what the issue is. There's an infinite number of decimal places. If I'm stuck after 35, how am I supposed to verify what happens in the rest of infinity? I can't. So, but there's still some ways I can study irrational numbers. There are some physical ways to go about, which is that, well, we could use some geometric and algebraic means to find some of these numbers. There are geometric constructions using which I can make irrational numbers. That's a very fun thing for me. So my notes ends here for now. I'm going to continue after a bit of study. So the numbers that I can make through geometric constructions, we call them constructible numbers. And by geometric constructions, I specifically mean using a compass and a straight edge. That's one version. So that's the geometric definition of constructible numbers. If I can somehow draw this number out as a length, I'm going to create a length that represents the number I want to represent, a length representing that number using a compass and a straight edge. Or equivalently, an algebraic definition for constructible numbers is I'm going to use some integers, right? I'll start off with integers and I'll do some basic operations: addition, subtraction, multiplication, division, and square roots. That's the limit. Square roots only. Using these operations, if I can create a number starting from integers, I'll call it a constructible number. So what are the numbers that we can like geometrically construct under these restrictions that I have described? Well, every square root ever, every integer square root. So let's go over to the board, right? So let's say I want to create the number root 2. How can I do that? Well, to start off, let's say you have a straight edge. Consider the length of your straight edge to be the unit based on which we will do the rest of our necessary calculations. Or yeah. So let's say that length is 1. Well, 1 is the same as root of 1. So we're done. That's the first number. If you ask me to find the root of 2, here's what I'll do. I'll draw a triangle, right? I'll draw a right angle triangle where the base and the height are both of length 1. And what happens to the hypotenuse? Well, this is a result from the theorem by Pythagoras that this is 1 square plus 1 square. This is root 2. Now, if you ask me, well, okay, fine. You created the number root 2. What about root 3? I'm supposed to create root 3. Here's what I do. I repeat the process. I'm going to take a height of length 1 using this hypotenuse of length root 2 as a base. I'll use this guy as a base. I'll join a line that shall be at the height of the rectangle. I join the endpoints of these two lines. And here is a triangle. Wait, let me draw this. Right? Okay. Now here is a triangle that satisfies the property that we need. What is the hypotenuse of this triangle? If not root 2 squared plus 1 squared. That's precisely 2 plus 1. That's precisely the root of 3. I can do this forever. So basically, here we have the root of 3, right? I just showed you how I can make the root of 3. I'll do it again. I'll do it again. I once again attach a line of length 1, and I'll make another right angle triangle using this hypotenuse of size root 3 as a base. And looky, what's this number? This length is precisely root 3 squared plus root 1 squared. That's 3 plus 1. That's root 4. I can do this forever. I'll attach another line of length 1. This has a length of root 4. So what's this length? This length is precisely root 4 squared, which is just 4, plus 1. This is root 5. I can do this forever and create every single root of every single integer there is. I can do that. So yeah, I could do that. And furthermore, I mean, it's obvious that I can create every single integer. How? Well, here's that unit length I talked about. This is 1. I'll draw another unit length next to it. There's 2. So yeah, in this manner, I can draw, well, not every single integer, but yeah, I can draw every single natural number out. I can do that. And let's say, given, if I had two constructible numbers given to me, like let's say I've done some constructions and I've made a certain length A, and I've made a certain length B. Well, I can now join those two numbers, whatever they may be, and draw the length A plus B. I could have them overlap. Like let's say A is larger and B is smaller. Like let's say this much. Like let's say this much is A, and this larger line, this portion is B. So this is the difference, right? This is the difference. I want the positive difference, basically. That's the length. So it has to be the positive difference, right? So that's the difference. And let's say you want me to find their product. I'll use the idea of similar triangles. If you want me to find the product, I'll use the idea of similar triangles as follows. So let's say I construct a triangle where this has the length A, this line has a length A, this line here will have a length 1. Then I'm going to extend the base. I'm going to extend the base until the base has extended to the length B. The idea of similar triangles tells me that, well, this larger triangle, right? This larger triangle that was formed by extending the smaller triangle has a base B times larger, right? The base is B times larger than the previous base. So this length by must also be B times larger. So that's A times B. And let's say, so basically, if I have two constructible numbers, I can create a length that is their product. And if you want their ratio, a length that is their ratio. Just a second. Yeah, so form the ratio. I'll take this length as A, right? And what's going to happen now? Well, I understand that the base is B times the base of the smaller triangle. Now let's think about the smaller triangle. Smaller triangle has a base B times smaller. So the smaller triangle will have a height B times smaller, as in I'll have to divide B to retrieve that height. So this height over here is the ratio.